Yeah, welcome back everybody to the post-lunch session. So I now request Professor Biplab Sanyal to chair this session.
First speaker is Professor Surajit Saha from Indian Institute of Science, Education and Research, Bhopal. And he's going to tell us about engineered 2D materials, the heterostructure effect.
Thank you, Professor Shanal, for the introduction. I know it's a big challenge, first of all, to not fall asleep, and that too after a nice lunch. And if you really wish to sleep, please go ahead, okay? So, okay, I start with acknowledging and thanking Arun for this kind of invitation and the organizers. It's a wonderful place to be here. Unfortunately, I had to really cut short my plan for some other reasons, but I would have loved to stay there for this long episode. It's a wonderful workshop, and hope in the future I'll be able to, be part of such workshops and stay longer. Thank you. All right, so we have been putting some effort on 2D materials for quite some time, and so recently we could see some interesting behaviors in 2D magnetic systems. So that's what is going to be part of my talk today. I titled it like Engineered 2D Materials, though, of course, whatever the heterostructure effect that I'm going to discuss, it's effectively applicable for even non-magnetic systems in one way or other. Here, I'm going to focus on 2D magnetic systems. These are a group of people. Actually, it's because of them the work is here. Most importantly, Shubhadeep, who spearheaded the problem. He did everything in and out. And then Shubhro was one who helped us, especially when we needed, what is going on. So he was one of the key, person who helped us. And then Devesh was another group member who was also important player in this. These are my group members. And most important other things, like without samples, we'll not be able to do anything. So some of the crystals, of course, we can procure, but not everything, right? So from IISc Pune, Luminita helped us with FEPS3, and Ravi from our department, he helped us with this interesting topological system MOT2. So I'll tell you the story behind this. All right, so this is for general people who may have some interest in looking for collaboration. We are open to that. So what we do is basically Raman scattering, and not to the level that, okay, whether my graphene is good or not, one layer or two layers, or just be happy with the characterization, but we want to go a little beyond, explore what all physics we can sort of dig out using Raman scattering. So we have a typical spectrometer from Horiba, and we have an attocube magnet. So we can vary temperatures roughly about helium temperature to all the way to 600-700 degrees Celsius. Okay, we have another cryostat also to work with, and we have 3 different lasers, so we can do some different activities as well apart from the regular studies. Okay, so now apart from the 2D things, so basically what type of problems that we always try to understand or address is look at the correlation effects through Raman scattering way. And of course, quantum material is one set of materials where we get to see many of such interesting behaviors. Now, one may ask, like, how come Raman will help you, right? So most of these systems, you see, have these 4 degrees of freedom: the spin, charge, lattice, and orbital. They sort of have, what do you call, a crosstalk among themselves. And if you see, one of them is the lattice, okay, which is basically the phonon, where Raman can be a part of it, right? And any interaction of these phonons with any of the other degrees of freedom can be sensed by the phonons, and that's where Raman can be helpful or useful. So this is what we try to dig all the time, and the various kinds of model systems that we work with is like there are series of transition metal oxides in 3-dimensional systems. For example, there are many multiferroics, there are spin liquid systems, frustrated magnets. There are many of such things which we are working on. And on the other hand, I have a separate group who is working on 2D systems, which are the layered materials, starting from graphene, transition TMDs basically, and then even now these 2D magnets. So we also try to create different kinds of heterostructures. We get to see some effects, and that's nice to go ahead with. Okay, now let's start with the business about 2D magnets. Of course, we have been hearing about 2D magnets, especially from 2016 onwards. More focus been given from around 2016 onwards, I would say, if I can sort of pinpoint. But if you see, the whole story goes back to almost about 1940s or a little around that time, where the theoretical models were started to be built up, and many understanding were actually obtained throughout the decades. These are some experimental observations, and then much more vigor actually came around post 2000. This is an interesting article. It's a review article. One may take a look at. Now, when we talk about 2D magnets, the first thing that comes to mind, when we talk about magnetism, obviously, can magnetism exist in 2D systems? Of course, now we know, but to begin with, there were many. If you look at the Marvin-Wagner theorem, it basically says that unless you have an isotropy, you cannot have long-range ordering in systems which are less than three-dimensional. In less than three-dimensional systems. So in 2D systems, the kind of spin interactions that we can think of, this is basically an isotropic system where spin can have the x, y, and z components. So that is that can be modeled through Heisenberg Hamiltonian. But then if there is an anisotropy, which is basically the easy plane anisotropy, if I say, so the spin can be actually in the plane. So it can have the x and y components, and this is the easy axis anisotropy, where basically you can think of the Ising model giving us the understanding. And there are DM interaction and then Kitaev interactions, which are also important players in 2D magnetic systems. Now, the magnetism in 2D systems may also be looked at in a different perspective, which is through Magnon picture, where one can sort of look at the Magnon density of states and see whether or not the long-range ordering will be allowed. So here are two different scenarios where if there is no easy axis anisotropy, there is no gap in the Magnon state, and therefore here the long-range ordering is basically not favored. But when there is there is an easy axis anisotropy, then there is a gap that that pops up, and there one may have a long-range ordering or a quasi-long-range ordering. Now, over the years, we have now witnessed various kinds of 2D layered materials showing ferromagnetic, antiferromagnetic ground states, which have the ordering temperatures across this wide range of values. So here you can see all those sort of examples where these are different notations to basically capture their perspectives in terms of magnetic state. And if we ask why are we looking at the 2D magnetic systems, these are one of the important applications that one can think of various kinds of spintronic devices. Here you can see there are some examples like the spin warp, the spin orbit torque devices, and then there are other FET and SO filter devices. There are many forms that one can think of if we really come up with good 2D magnet. Now, so 2D magnets, of course, magnetism people have been studying in 3 dimensions, but when it comes to 2D, there are some challenges how to probe them, right? Not all the bulk techniques will be useful. For example, if we have the usual magnetization measurement with the discrete type of systems, it's difficult to measure 2D systems. It's a challenging stuff. So there are some techniques, and only a few of them I have listed here. There are a handful of people in India who are working on some of these techniques, and some of them probably we're still to start with. For example, this what we call the Envy Center-based ODMR technique. There are now a few groups in India who are setting up one in our IISc as well. One of our colleagues is trying to set up. So he's working on, his name is Fani Kumar, he's trying to set up. And then there are other techniques which can also be a very important player in understanding and probing the 2D magnets. And at the end, where I sort of can be of some help is Raman and photoluminescence, basically looking at the excitons and others and other transitions. So that's where we try to look for. So there's another technique which can be very useful. Now, for the students' sake, I have kept a few slides to sort of convince that, yes, indeed, Raman can be useful to capture the magnetic states even in 2D. So Raman scattering is basically an inelastic scattering of light where we shine some electromagnetic radiation, and that electromagnetic radiation, basically the photon, interacts with the material that is under study, and it excites the system, right? And when it excites the system, electron-hole pair is created, and then there is an exchange of energy between the material and the photon, which is the incident photon. So the consequence of the interaction is it comes out, basically an exchange of energy with the phonons or other excitations. And then at the end, there will be a scattered light, which we probe them. And then basically, compare the incident light and the scattered light, and then come up with the stories that it can have. There are these conservation laws that has to be followed. Important thing is this is a non-destructive technique, so these are some added advantage that it provides. And this is very sensitive to any deformations or any changes that we make in the crystal structure or any other association with the vibrations. So one simple way to start with is a harmonic oscillator model. But then, there are limitations with the harmonic oscillator model. One cannot really explain the physics of the phonons if we just take what you call the harmonic oscillator model, right? For example, we cannot explain the thermal expansion, okay? Simple basic stuff. So we have to start thinking of beyond harmonic oscillator model, and then maybe the good starting point is, the phonon-phonon interaction, which is basically, the starting point of the n-harmonicity. And when we invoke n-harmonicity, we can start explaining how the phonon frequencies would behave to various kinds of perturbation. For example, let's say temperature. Okay, so a typical n-harmonic behavior of phonon frequency would be, let's say, if I increase the temperature. So this basically, at the very low temperature, it mimics like a harmonic oscillator. Okay, it's almost like independent of temperature. And then as you go beyond certain temperature, it starts to fall. It is almost like a linear dependence here. But the whole function is sort of a, what do you call, it's a cubic and harmonic model. And similarly, the line width also shows a behavior something like this. Okay, so this is a typical behavior of an harmonic system in terms of phonons. Now, anything that is beyond this behavior, where let's say a vibration or a phonon is interacting with other degrees of freedom. If I remind you that we talked about orbitals, we talked about spins, we talked about electrons, right? Then the phonons would start to show some signatures. Of course, we have to be able to pinpoint that particular phonon or that set of phonons which are having the interactions. So for example, electron-phonon coupling, we know we have been studying about superconductivity, the Cooper pairs, right? The electron-phonon coupling as an important ingredient for superconductivity. So electron-phonon coupling is something that can be looked at using this Raman scattering. Then spin-phonon coupling is also that can be looked at. And basically, we're looking at this network of interactions, right? All right. Now, the simple picture that one can think of, you can choose the, what you call the spring ball model, and one can write the equation of motion, and then effectively, you can see that, okay, this is what the equation looks like, and the solution will give you a frequency which depends on the spring constant K and the effective mass mu, okay? So, in a very simplistic picture, if there is any change in the spring constant or the effective mass, the frequency is going to respond. Okay? That's what is the ballgame, all about everything. So now, what all scenarios can actually make changes to this? So here is a list of, not the entire. So it can be sensitive to many things. For example, any internal or external perturbations that we can think of, stoichiometry, doping, strain, pressure, interaction with charges, spins, orbitals, and many other things. Okay, there are a whole plethora of possibilities that can actually change the spring constant and even the effective mass. All right, so at the end, if we just work through all these simple equations, we find that there will be a set of not just the what you call the incident light information, but also informations which are different from the incident light, which is what we call the Stokes and anti-Stokes. all right? So with that, now if I have a spectrum which typically would look like some peaks, okay, it might be boring for some people, that's okay, but there are certain peaks, and then these peaks carry the important information that we're looking for. Now, what are the information that we can get? Let's say every peak has 3 important parameters. One is the central position, the peak frequency, which is what we call, which basically tells us about, let's say, the phonon frequency, or if you're looking at magnon, so that gives us the magnon energy, and if any other thing, any other excitation that we're looking at, it basically tells us about the energy of that excitation. Then it has the line width, which basically goes inversely with the lifetime, right? And it also has what we call the area under the curve, okay? And that area under the curve basically gives us the population. For example, if you're talking about phonons, so that goes in proportion with the phonon population or phonon density of state. All right, so these 3 parameters will help us to understand what is happening. Okay, so this is basically to say that the frequency would respond if we're looking at the what do you call the enharmonic behavior. Similarly with pressure also, it basically changes in the frequency in this fashion. Now, the fun lies when we see a deviation from such a behavior. Okay, that's what we look for. Let's see if there is any change, any difference from the expected trend. Okay, that's what our eyes always try to look for. All right, so let's say if we are using temperature as the variable, okay, and we're looking at how the frequencies would change as a function of temperature. These are the possible effects which can be incorporated in the overall frequency change due to the temperature change. So one is certainly the enharmonicity, which I said, and the enharmonicity will behave in this form. But then apart from that, if the system has electron-phonon coupling, so there will be some contribution from that. If that system has spin-phonon coupling, then it also has some contribution. So because of these contributions, there will be a deviation in the behavior of due to the enharmonicity. That's what we try to capture. And okay, spin-phonon coupling basically can be sort of understood as what we call the spin-spin interaction, and there is a factor which is basically the spin-phonon coupling coefficient or constant, and that's what helps us to quantify to a certain extent. All right, now I come to the systems that we have studied. We have studied this, what do you call, the transition metal phosphorus trisulfide systems, which are basically the manganese phosphorus trisulfide, FePS3, and IPS3. If you look at the crystal structure, this is just a one layer. Of course, if I have to build the structure, I need to have at least 2 layers of it, because at monolayer level, the crystal symmetry changes, okay? So whatever data that I'm going to show are not monolayer, but above that, okay? Now, if we look at the magnetic state, so all the 3 systems are antiferromagnetic at below certain temperature. So here are the data which is magnetization, the susceptibility data measured on bulk crystals of these 3 systems, okay? So here the top one is MnPS3. You can see this susceptibility trend, and right around 80K there is this magnetic ordering. Okay, below 80K it goes to antiferromagnetic state. For FePS3 is somewhere around 115K, below which it becomes antiferromagnetic, and for NiPS3 it's roughly about 150 Kelvin. These are the 3 different temperatures below which these 3 systems become antiferromagnetic. And if we look at the spin orientations, now see, in MnPS3 the next neighbors are antiparallel, all right? FePS3, this set of 3, okay, they are ferromagnetically ordered, and this set of 3 are ferromagnetic ordered, but compared to each other they're antiparallel. So if you look at the chain, there is a zigzag chain which is ferromagnetic, there is another zigzag chain which is ferromagnetic, but these 2 ferromagnetic chains are antiparallel, and that's what gives the antiferromagnetism in FePS3. Similar is the case for NiPS3, but here the spins are in plane, okay? In the other 2 cases, they're out of plane, and here it is in plane, and that's where the story is all about. Now, before I head out, so I showed in the previous slide the bulk measurement to assure you that there is indeed antiferromagnetic ordering, and to tell you the antiferromagnetic ordering temperature, the nail temperatures, right? Now, how do we know that there's something happening in Raman? So here is the first example of MNPS3. So MNPS3 has let's say this is room temperature data, the red one, and this is the low temperature 5 Kelvin data. Now, the main focus, the rest of the modes basically behave very similar way. There are certain signatures. We are not really, putting much effort on that. The most important signature is in this mode, which is the P2 mode, and also the P1 mode. If you see, I mean, they are very, very weak, right? And that's fun to be with them. So P2 mode shows a slight shift when it goes to the antiferromagnetic phase, all right? And P1 also shows a similar kind of a behavior. So here, what I'm trying to tell you, this is the color map where temperature versus frequency of this P2 is captured, and also the color basically tells us the intensity of the mode. You can see very clearly this is almost constant above the nil temperature in the paramagnetic phase, and below the nil temperature, it has shifted to this value. Okay, this shift is the signature in Raman for the antiferromagnetic transition. I hope I could convince you. There are already studies which have already sort of established this. Now in FEPS3, something different happens. Remember the spin chain, right? It's a zigzag chain. So because of that, the signatures of the antiferromagnetic ordering is different compared to the MNPS3. Here what happens is, the F1 mode, the lowest frequency mode in this spectrum, splits into 4 components. Why it happens? There's something called zone folding. If you look at the crystal structure, you have certain ordering of the atoms, but now if you work on the magnets, okay, the set of magnets, so when the magnets are turned on, now you have a different magnetic lattice. So the 2 different lattices are basically, the structures are different, and now if you work on the zone boundary, the Brillouin zones of the magnetic structure and the crystal structure, you will find that the 2 will basically fold with each other. So the zone folding basically gives rise to 4 modes at the zone center, okay? Which is what the signature of this magnetic transition in FEPS3 from 1 component to 4 different components. And here is the color map. To tell you that this is the temperature at which this transition happens. So this is the paramagnetic phase, and this is the antiferromagnetic phase, where you see this broad feature. Basically, there are these multiple peaks. So we're just plotting these 2 here, just to ensure that we see clearly. All right. Then NIPS3. So NIPS3 has very clear 2 different signatures of the antiferromagnetic ordering. One is in the form of magnon, rather 2 magnon, which is a broad hump seen somewhere around 500, 600 wave numbers at low temperatures. And that has a very interesting story. If I get time, I'll probably touch upon on that. Now, as we go to higher temperature, of course, you see it has decayed significantly. But at the same time, there is another mode, which is the N2, the second one here. Okay, that shows slight asymmetry, and it shows a splitting. Okay, so those are the 2 signatures which basically people look for the antiferromagnetic ordering. There were some there was a report which basically also said that the monolayer doesn't show antiferromagnetic ordering, and Raman was one of the tool, but then NTU group, Chiwa-Xiong, they did an extensive study and showed that even in monolayer there is antiferromagnetic ordering. And so the previous observations were a little inconclusive, mainly because if you look at the monolayer crystal symmetry and the bilayer onwards crystal symmetry, they're different. And just because of the crystal symmetry, the Raman signature becomes slightly different, and that's where one has to be very careful about. Okay, so anyway, the point is even NIPS3 also has magnetic ordering even at single layer, okay? And the signatures are in the form of this magnon and the peak splitting. So if we plot the phonon modes, so for example, here we're plotting this N2. So now you see this straight line is basically the behavior of the enharmonic trend, if I sort of remind you. So this is that enharmonic trend, and there is a deviation which is happening right around 150 K, which is the antiferromagnetic ordering temperature. So this becomes our indicator of the magnetic ordering. So we basically now will look at what happens if we thin down. Okay, it's not that something we're doing for the first time. We're basically establishing it again. So this shows that doesn't matter how thick or thin of MnPs3, FePs3, NiPs3 we take, the antiferromagnetic ordering or the magnetism is extremely robust. It doesn't matter, it doesn't change at all, okay? At least not to the level where we can really perceive. So here the Raman data shows starting from about 250 nanometer thick, okay, very thick, then about 100 something, about 14 nanometer, 5 nanometer, you can see this transition is right at that same temperature, okay? And this has again been established by some people in literature. FePs3 also has the same story. The magnetism is very robust. It doesn't matter how thick or thin we work with. So here is example of 50 nanometer, 10 nanometer, all of them are showing the same transition temperature. NiPs3 also the same, okay? Then we wanted to sort of find out ways if we can make some changes to these magnetic interactions that are happening in these three systems. So Shubhadeep was very, I'm really happy about this guy. So yeah, so then he started playing with MOTE2. So MOTE2 is another system which is not the 2H phase, but the 1T prime phase, okay? MOTE2 at room temperature, specifically above 250 Kelvin, is a spin Hall system, and below 250 Kelvin, it's a Weil semi-metal, okay? So it's a topologically very interesting substance, very interesting 2D material, which is what he worked, and we have some stories about that as well. Now, what he did, he created a heterostructure of MnPs3 on top of MOTE2, and he tried to understand what is happening in the magnetic response. Now you see, so this is without the without the MOTE2 in between. This is just the MnPs3. We're showing here about 100 something nanometer thick. As usual, it's robust. It shows the transition around 80K. But now thicker sample put on MOTE2, you see where the transition is happening, somewhere around 30-40 Kelvin, 35 Kelvin. So the 80 Kelvin Néel temperature has gone down to about 30-35 Kelvin, even for thick samples. Okay. Now, if we reduce the thickness to about half of it, we are not able to see the transition. Our lowest temperature was 5 Kelvin. So we believe, even if the transition is happening, it could be below 5K or just around 5K. All right. And going below this thickness was not useful. We did that, of course, we couldn't see anything. All right. So at least the first observations tell us that if we put MnPs3 now on something which is, let's say, MOTE2, there's something happening. Some engineering is happening in the magnetic interactions. Then we looked at the other 2D systems, the FePs3 and NiPs3. Let's look at it. So this is FePs3 on just the silicon substrate, no change in the magnetic ordering temperature. Here with MOTE2 underneath, now you see that 110 or 115K has gone down to about 80K for about 50 nanometer thick FePs3. And if we go to about 2023, it has gone further down about 70-75. So there is a lowering of the Néel temperature even for FePs3. NiPs3, now that was the game changer. This guy is extremely robust. Okay, so this is all with MOTE2. Now we are showing as different thicknesses that we could do. I mean, thicker sample has no response. Even intermediate one, 44, 33, 12 nanometer, they are still robust in terms of the Néel ordering. Okay. The question is, if MnPs3, FePs3 showed lowering of the Néel temperature, why not NiPs3? So that's where Shubhru was very helpful. So we looked at and we figured out many different ways, and we explored different experiments now, not just with MOTE2, but with other topological systems, for example, SB2TE3. Then we tried with gold as a thin layer of gold below MnPs3 and thin layer of copper below MnPs3. Why? Okay, MOTE2 is a Weil semi-metal which has a strong SOC and has surface state. Okay, these two are the important players which we came up after the discussion with Shubhro. And then we explored, okay, Sb2T3, it shows the same stories, it shows the reduction. So here we're plotting the nil temperature when we put on silicon, when we put on MOT2, when we put on Sb2T3, gold and copper. Copper, you see, it has completely quenched the magnetic ordering. Okay, so there is some role of the surface state, or shall I say the charge density that we have at the interface. Okay, so it basically completely quenches the magnetic ordering. For gold, we see some thickness dependence, but again, it has lowered the nil temperature, and Sb2T3 and MO2Te2, so they just lower the temperature, and for very thin MnPs3, it quenches. Okay, so from all these sort of experiments, we could at least establish to an extent that there is a role of SOC and there is a role of charge density of state. So there are other theoretical models which were also published by then, and we tried to look at whether those are the possibilities. Here we are taking the reductionist approach, and we see if strain and charge transfer could be an important player. Just to remind you, these systems are not metallic. These systems are somewhat insulating. They have a gap of about 1.8 electron volt approximately. Okay, so there we sort of believe that charge transfer is not really playing much role, but I'll try to convince you why. So strain we rule out because if there is a strain, then we should be able to see signature in the phonon frequency shifts, which is what is missing in our cases. So as you can see the data, we don't see any change in the frequency values irrespective of the thickness. Okay, if there is a strain, so the strain will be maximum for thinner samples and will reduce as we go thicker and thicker, and therefore effectively we should be able to see a change in the phonon frequencies and would tell us there is strain or not. From these set of data, we can sort of confidently rule out that there is no strain, at least not at the level where we can perceive. Then about charge transfer, so this is the calculation by Chichari, and they showed that if we have sufficiently high charge dopings, which is on the order of about 10 to the 14 per cm square, then it can actually switch from AFM to FM, ferromagnetic ordering. So there was something we also had in mind, whether there is some other changes happening because of charge transfer or anything. But such degree of charge transfer is not possible without any bias or any other external mechanism. So we just did a plain experiment without any bias or anything. All right, and being an insulating system, or if I say semiconducting system, such a huge charge transfer was not feasible. So we rule out that. Now the other two possibilities, as I was just pointing, the SOC and the spin orientation. So spin orientation, to remind you that for the MnPs3 and FePs3, the spins are out of plane, okay, it's vertical, and for NiPs3, the spins are in plane. So what we think is the underlayer has a large spin orbit coupling, and that introduces DM interaction in the spins or the spin interactions which are in the magnetic layer, and therefore there is a canting in the spin, okay, and that eventually loses its magnetic ordering, which is what we believe we proposed, and that also helped us with the understanding of what you call the spin orientations. So here you can see for MnPs3 and FePs3, the spins are out of plane and the DM vector is in plane. So therefore, the effective Hamiltonian will give you non-zero DM interaction. But for NiPs3, the spins are also in plane. Therefore, all the vectors are in plane and they cancel out. Okay, so that's why in NiPs3, we could not see any response even after putting on the substrates that we wanted to, but only for these two systems. So that basically sort of positively guides us, okay, there must be something DM interaction getting invoked, which is why this suppression of the magnetic ordering is happening. And at the same time, since we could see that different substrates having different charge density of states are also playing a role to the degree of suppression of the nil temperature. So we believe even charge density of states are important player apart from the SOC and the magnetic, the orientation, the spin orientations. So, so these are the two important factors that we learned. The spin orientation is an important player and the electron density of state is another important player in deciding whether or not the spin interactions could be tailored. And here is why we see. So this is the take-home message from this sort of experiment, that we learned that the SOC is an important player, and the electronic density of states is also deciding importantly. Now, I said if I have some time, do I have about 5 minutes? Okay. So I'll then quickly talk about NIPS3, which is predominantly the work of Devesh, the other guy, which I was telling. So he looked at NIPS3 a little more in detail, and what he saw was that, okay, the previous work establishes that NIPS3 is antiferromagnetic below 150 K, and one of the key signatures was the presence of the 2 magnon in the spectrum, which is the broad feature. Now, as we go to higher and higher temperature, this magnon basically gets sort of almost quenched, okay? But he wanted to dig a little more into that. So what he saw that at room temperature also there is some, some signal about the 2 magnon, which is not something that one should be neglecting. He did not neglect, which is why I think we have a story now. So this is the 2 magnon at low temperature, and the NTU group, Chia-Sheung's group, they also discussed that this 2 magnon they could see up to about 290 Kelvin. Now, this is something very important point to be noted. Anything related to magnon that is present above the nil temperature is something interesting. One has to really think why. Okay, so these are the data, and what he saw was that if you remember this P2 peak, which was the signature for our antiferromagnetic ordering, so that shows an asymmetric behavior, and this asymmetric behavior, interestingly, is absent at very low temperatures. It starts to pop up somewhere around the antiferromagnetic ordering, and it becomes more important and vigorous at higher temperatures when it is not antiferromagnetic. Okay, so this is what it is, and this he basically tried to understand with Fano asymmetry, and then the story is, so here you can see. Now, if you look at the spectra as a function of temperature, so right around 80 K, the 2 magnon is somewhere close to about 600 wave number, and as we go to higher and higher temperature, you see how much it shifts. It goes almost to about 250 or 300 wave number. It's a large shift, okay, and that is what is captured here. The corresponding line width is, so this is the frequency and this is the line width. They are captured here, and this is the intensity. The intensity also sort of increases. So people earlier reported only in this range. Now he's found that the what you call the integrated intensity, basically the area under the curve, that also keeps on increasing. Now this is a neutron study which basically said the 2 magnon was present even at higher temperature above nil temperature. And there, then from the asymmetric parameter, he figured out that there is a coupling of that phonon with this magnon. Okay. Now, so at low temperature, this peak is far away from this peak, the magnon peak. Hence, there is no coupling. But as the temperature rises, it approaches and goes almost to P2. And that's where the coupling becomes more and more. It's like a coupling between a discrete state and a continuum state. The continuum is basically the magnon signal here. And this, there were discussions whether it's really because of the coupling with the 2 magnon or something else. The paper is still under review. We got the report and looks positive. Let's see. So here we have a more convincing result to show that this asymmetry has something to do with the magnetic degree of freedom. How? So we plot here the susceptibility, and the susceptibility, up to about 600 Kelvin, which is 4 times the nil temperature, you see. So the susceptibility, you see, it is still, it doesn't show like what you call the 1 by T behavior, okay. This still has, the tail is still not starting here. So, and the coupling, it basically follows the same behavior as the susceptibility. So these 2 correlations make us sort of, convinced that there is indeed a relation between the 2 magnon and this phonon, which is what is giving this asymmetry. So I think with this, I'll stop here. We learned that in NIPS3, the 2 magnon has a very interesting story to give us, and that persists even very, very high temperature, and we believe there is something like paramagnon present in this system. So.
Thank you very much for a very exciting talk. And also many thanks for keeping the time exactly. Questions, comments from the audience? Yes, please.
This is just quick question. How a magnon is, the presence of a magnon is indicated as a broad peak in the Raman spectrum?
Okay, so if
How
it is a
it's
first order
originated?
magnon, then it will be a sharp peak. And typically, it will be at a low frequency, typically. But when you see a broad peak, it means it's a higher order magnon. So that's why, I mean, in NIPST that we see, it's a 2 magnon. So it's a second order magnon. And second order phonons, magnons, or any excitations will typically be broader, mainly because there are several Q factors, I mean, Q contributions are coming, momentum.
Another one question is, when you do temperature dependent measurement, are you doing in vacuum or
Yes, it is.
it's in vacuum?
Yeah.
Okay, thank you.
Nice results. I just have 2 questions, maybe they're very silly. So when you had
No
the,
question is silly.
well, you would
Sorry.
understand as soon as I pose probably. So when the topological insulator was underneath, so when you had this hybrid structure of your antiferromagnet and the topological insulator, did you also do the susceptibility measurements and did you see any changes over there?
No, that is not something possible, at least not at our level, because susceptibility, what we measure is the squid systems, the vibration, the VSM systems. And there only the bulk measurements are taken. Here so the samples we have is antiferromagnetic, so the signal will be almost non-perceivable. And then we have a strong diamagnetic silicon. So it will basically kill everything.
Okay.
We cannot do bulk measurement.
So because for these topological insulators, you mentioned the surface states, and one of the signatures is to look into the spin momentum locking. So since you have an antiferromagnet, did you try the Hall configurations, the anomalous Hall, to understand if there is this spin momentum locking?
No, we didn't try. I mean, we have limitations, so we couldn't try. So our colleague is trying to look at, I mean, hopefully, once things are ready, then we'll be able to look at through this NV Center technique. Let's see.
More questions? Yes, please.
Yeah, I liked your introduction. Very nice tutorial there almost. I have a couple of questions. One is, when you label all these peaks for a magnetic system, typically we label them with irreps from the character table. So here you're just labeling them as F1, F2, F3, and so on and so forth. How are you calculating the number of modes, and how should it really be labeled? Do you consider magnetic groups, or?
Shall I answer that question?
Yeah, please.
Okay, so yeah, the labeling, we kept it at the simpler level so that the readers or anyone in the audience doesn't have to really bother about the symmetry and other. Those things are in the table so I didn't show that. So each of these modes either have the asymmetry or B-type symmetry. So that is what the symmetry notations that we know. We also do polarization dependence and we figure out what the symmetries are. And we tally with the literature informations as well and figure out if any differences are there. So those symmetry informations are there. It's just that I didn't put in that slide.
Did you consider the magnetic group for it or the crystallographic group?
Okay, the magnetic group we did not consider. Just the fact that in FEPS3 we could see a sort of more number of modes which could be explained by the zone folding. So we were sort of happy with that. Yes, I agree. One should also consider the magnetic group and look at more. We didn't do that.
So the other question I have is the suppression of the antiferromagnetic transition. So why would Dialogen-Schimoria interaction suppress the transition entirely? I would just imagine.
Okay, so I just had one Arun, which basically sort of, so this, let's say the antiferromagnetic ordering that we have to start with, and then the DM interaction, what basically makes it, so if you think of, let's say these two spins are antiferromagnetically ordered, and here is this D vector, right? So it will act on the two spins, and then eventually they will be canted. So depending on the degree of the D vector, the canting could be more. And hence the SOC is an important player. If the SOC is high, the D vector could be high. That's how it scales. So the stronger the D vector, the canting could be higher and higher. And we believe when you
Right.
go to
So if the canting is, why would canting suppress the transition?
Excuse me, maybe we should
Maybe you're right.
should continue
Yeah,
the
maybe we'll
discussion
continue
in
later.
the coffee break.
Yeah.
The very last question, please.
Yeah, very interesting results. So actually, my question was related to what he just asked. So is there an understanding about what is the spatial extent to which this DMI interaction is important? Because I think even in your 144 nanometer sample, you are seeing significant or probably full suppression of your Neal temperature.
I'm not sure if you were also one of the reviewers. So that was a typical question.
No, I was not.
Yeah. So what I'm trying to say that this is a very typical question. The extent to which the DM interaction can really be seen or can be influential is probably not many layers, and our samples are thick enough to sort of defy that. But the fact is we see, and we don't have any other better understanding than the DM model. Let me be very frank. So with the DM model, we could sort of differentiate and make some understanding of the MN, FE, and also the NI. Because they three have differences in their own behavior. And with that interaction, we could sort of at least have some first level of understanding. Yes, one has to really probe. So in fact, so shall I stop?
Kind of.
I'll tell you more details.
Yes, because let's thank the speaker once again for a very nice talk. Thank you.